Good morning, students. This is Dr. V. Sivanagaraju from IARE. Today, we are going to discuss digital modulation techniques. In that digital modulation techniques, what are the types? And in that, we are going to discuss ASK modulator and detector. So, firstly, what is modulation and how modulation is done in digital communication? So that's what we are going to discuss. So this topic will cover in module 4. So module 4 is mapped with CO4. So the CO4 is analyze the digital passband communication schemes like ASK, PSK, FSK using modulation and demodulation process. So this module will cover all the digital modulation techniques clearly. Okay, so let us start the topic. So first we'll start with the introduction. So we'll start with the baseband. Baseband signal means original signal. So just like M of t is our message signal. So it is a baseband signal. So these baseband signals have sizable power at low frequencies. They are suitable for transmission over a pair of wires or coaxial cables. So baseband signals cannot be transmitted over radio link because this would require impractically large antennas to efficiently radiate the low frequency spectrum of the signal. So already we discussed baseband means original signals. The original signal means it is in very low frequency. Such low frequency is going to transmit over radio link, means it is impractical. Why? You know that the relation C is equal to F lambda. By using that C by F. So you know the C is the velocity of the light. So it is 3 to 10 power meters per second. And frequency. So here the frequency is in kilohertz, where it is in baseband. So roughly you can take some 30 kilohertz. So 30, 10 power 3. So here you will cancel 4 times and 3. So it is 10 to the power of 4 meters. 4 meters means it is in 10 kilometers. So such height is impracticable to place the antenna. So we are going to modulate. Okay. So after modulation, this baseband will convert into passband, or simply called as band pass. So baseband signals are not suitable for radio link. That's why we are going to that modulation. So you know the term modulation. Modulation means varying the sum of the characteristics of the carrier signal in accordance with the instantaneous value of the message signal. So that is the basic definition of the modulation. So in binary modulation schemes, the modulation process corresponds to switching or keying the amplitude, frequency or phase of the continuous wave carrier between either of two values corresponding to binary symbols 0 and 1. So that means here the binary data is 0 and 1. So this is my incoming data. According to the incoming data, my carrier will going to switch in amplitude, frequency or phase. Any of these 1, it is going to vary. Okay, so this is in digital communications. This will happen in digital communications. So the three types of digital modulation techniques are amplitude shift keying, frequency shift keying, and phase shift keying. So we are having three types of digital modulation techniques. We are having three types of digital modulation techniques out there. One is ASK, simply you can call as ASK, FSK, frequency shift, and PSK, phase shift keying. Okay. So here we can see how that ASK waveform, that means amplitude shift keying. So here the input binary sequence 1 0 1 1 0 1 0 1 1 1. So that is my incoming data, where the below one is the carrier, continuous wave carrier signal. Wave that carries a high frequency signal. So according to that input data, my carrier is switching between either amplitude, phase, or frequency. So in ASK, here you can see where 1 is present, at that the signal is present. At 0, it is absent. You can see. So that is amplitude switch keying. So another name, or you can call it as on-off switching also. That means here you can see if 1 is coming, the carrier is presented as. At 0, there is no signal. So it is absent. On, signal is present. Off, signal is absent. So in some way you can call it as on-off keying also. So according to the digital communication system, is said to be coherent or non-coherent. So here the detection of the digital communication. Here the detection of digital communication can be taken as in two varieties. One is coherent and another is non-coherent. So another name is coherent is a synchronous and it is non-synchronous. So we can detect the signal in digital communication either in coherent way or in non-coherent way. So in the coherent, if the receiver is synchronized to the transmitter with respect to the carrier phase, that means here the receiver must be synchronized with the carrier of the transmitter. Then we can call it as coherent. Or otherwise, the system is said to be non-coherent. So naturally, a non-coherent system offers the practical advantage of reduced complexity, but at the cost of degraded performance. Why? So the coherent is very costly. The main disadvantage of coherent is costly. So it is costly. Whereas non-coherent, it is cost effective, economic. But the disadvantage of this non-coherent is probability of error is more. So by using non-coherent, you are getting more errors. That is a probability of error. Okay. So here C of t is the carrier, which is equal to AC cos 2 pi FC FCT plus pi C. So where AC is the carrier amplitude, FC is the carrier frequency, and pi C is the carrier phase. So given these three parameters of the carrier, we may now identify three different forms of binary modulation. modulation. So nothing but ASK, PSK, FSK. So the first one is BSK, binary amplitude shift keying, simply ASK, in which the carrier frequency and carrier phase are both maintained constant, while the carrier amplitude is keyed between the two possible values used to represent symbols 0 and 1. Why? Because if any analog signal having three parameters, one is amplitude, second one is phase, and third one is time or frequency. Time or frequency. So here my aim is amplitude shifting. So here the remaining two, phase and frequency, both kept constant. So I am going to varying this amplitude only. I am varying only the amplitude. So this carrier amplitude is keyed between the two possible values is to represent symbols 0 and 1. Why? My data is in digital form, binary form. So the carrier amplitude is switching between 0 and 1 only. Whereas the second one, binary phase shift keying, here the carrier amplitude and frequency are both maintained constant, while the carrier phase is keyed between the two possible values used to represent symbols 0 and 1. So here the phase having two possible values, that is 0 and 180 degrees. That means here it having the opposite phase to symbol 1 and 0. That means, for example, here the phase is keying for 1 is 0 degrees and 180 degrees for symbol 0, that is BPSK. And another one is BFSK, binary frequency shift key, in which the carrier amplitude and carrier phase are both maintained constant, while the carrier frequency is keyed between the two possible values issued to represent symbols 0 and 1. So among the three, two kept constant. The another one is going to keyed between the two possible values. Okay. So now the BSK. So binary amplitude shift keying is one of the earliest forms of digital modulation techniques used in radio telegraphy at the beginning of the 20th century. So this is the basic one or started one. So to formally describe ASK, consider a binary data stream B of t, which is of the on-off signaling variety. That is, B of t can be defined as root EB for binary symbol 1 and 0 for symbol 0. So here EB is the energy per bit. Energy per bit. BT is the binary data stream. And this S of t. S of t means modulated signal. So I am going to modulate this baseband signal with the carrier. Then I got the passband or modulated signal. So here multiplying B of t by the sinusoidal carrier wave of the phase pi c set equal to 0 for convenience of representation. So simply we can write S of t, which is equal to square root of 2 EB by TB cos 2 pi FCT for symbol 1 and symbol 0 and 0 for symbol 0. That means here I am giving amplitude only for symbol 1. There is no amplitude for symbol 0. So that is the main theme of this BASK, binary amplitude shift key. So here, when a bit duration is occupied by symbol 1, the transmitted signal energy is EB. When the bit duration is occupied by symbol 0, the transmitted signal energy is 0. So that's what we discussed in earlier, that S of t is equal to square root of 2EB by TB cos 2 pi FCT for symbol 1, whereas 0 for symbol 0. So on this basis, we may express the average transmitted signal energy is E average is equal to EB by 2. So EB is the energy per bit. So EB is energy per bit. So this is energy per bit. So here I'm taking that transmitter. So how this transmitter is formed? So this is a product modulator, and this is my carrier. So this is the binary signal, and this is my binary ASK. So this is my binary ASK. So here B of t is nothing but some data. For example, it is 0, 1, 0, 1, 0, 1, this one. So this is coming, and the carrier is here, the continuous signal, continuous wave. So after the multiply of this B of t with C of t, the carrier, you can represent as C of t. The produced one is S of t. So mathematically, here you can represent as 2EB by TB cos 2 pi FCT. Here the for simplicity phase is taken as 0, and this is 0 for symbol 1, and this is for symbol 0. This is for symbol 0. But graphically, here we can say this is 0, 1, 0, 1, again 0, 1. So when you take in this intervals, here for 0 there is no signal, but for 1 we get again 0, and this one amplitude, and this is 0, and this is like this. Okay, so here, whereas the symbol 1, the signal will present, and for symbol 0 there is no signal. So this is my transmitter. So it is very simple one. So just the product modulator, which is going to multiply both the signals B of t and C of t. So here I can take in that NRZ representation, NRZ formation, NRZ format for representation of this data, binary data. Okay. So here the ASK modulated block diagram comprises of the carrier signal generator, the binary sequence from the message signal, and the band limited filter. So the carrier generator sends a continuous high frequency carrier. The binary sequence from the message signal makes the unipolar input to either high or low. Okay, to either high or low. And now demodulator. So here we're having two types of ASK demodulation techniques. Already we discussed, that is asynchronous or synchronous. So in synchronous, the clock frequency at the transmitter when matches the clock frequency at the receiver, it is known as a synchronous method. Or the receiver which is synchronized with the transmitter carrier are also called as synchronous. Whereas asynchronous, so there is no need of this synchronization between the receiver and transmitter. Then we can call as asynchronous or non-coherent. Okay. So for this, here I am taking that how to detect this binary ASK. Integral 0 to dB dt. This is decision device, and it having some threshold, which is cos 2 pi of ct, and ASK. This is my receiver. So before going to receiver, where we can represent the signal in a signal space diagram. So for ASK, here we taken as the basis function phi1 of t, and here there is a decision or the separation between symbol 1 and symbol 0. So symbol 0 is represented as 0 and symbol 1 is represented root EB. So my modulated signal is represented as S of t. So that can be represented as root EB pi 1 of t. So here pi 1 of t is the orthonormal basis function. So it is represented as root square root of 2 by dB cos 2 pi fct. So finally, S of t is equal to square root of 2 EB by dB cos 2 pi fct for symbol 1. For symbol 0, it's simply 0. Why? Here in previously you can see the transmitter having the product modulator, which is going to multiply this B of t. B of t is the binary data which is going to multiply with the carrier. So we got the S of t, that is the modulated signal. So S of t is this one. So this is for symbol 1. So here in receiver, I am going to receive this S of t. I am going to receive this S of t. So S of t is again here square root of 2 EB by TB cos 2 pi fct is coming with noise. But here I am not showing the noise signal. Just I am taking only the modulated signal. That is nothing but my ASK. This is my ASK, amplitude shift keying signal. So again here also having that product modulator and this integrator and with a decision making device. So after multiplication of this incoming signal, that is a received signal, with the cos 2 pi fct, so the cos term is going to square. Okay, and this is going to apply to the integrator. So already know that integrator is nothing but a low pass filter. So that low pass filter which allows the low frequency signals and attenuates the high frequency signal. So here we got that square term. So that can be, we can treat it as a high frequency signal. Why here FC term is there. So FC means carrier frequency. So already you know that baseband signal is a low frequency signal, whereas the carrier is the high frequency and high amplitude signal. So that's why here we can square that frequency, means getting more signal. So my low pass filter allows only the message signal. That means low frequency. So the baseband is generally a low frequency signal. So it coming to the decision making device in one way. In another way, here we are using transmitter at orthonormal basis function, that is pi 1 of t. So this pi 1 of t is going to multiply with the same number. It gives the normalized value. So that means it gives only 1. Normalized means 1. Okay, that is you can know integral 0 to tb pi I of t and pi j of t dt is equal to 1, 0. So 1 is for I equal to j. For I not equal to j, it produces orthogonal value. That means 0. They both are orthogonal, it produces 0 value. If they both are equal, it produces the normalized value. That means 1. So in that way, here this integrator filters this total basis function and allows this root EB term. Only root EB term will come out of this integrator. So this value is applied to the decision making device. So the decision making device which makes the decision, and decision making device having some threshold. So threshold may be taken as some 0 volts. 0 volts. So generally the root dB means some amplitude level. So it may be more than 0. So generally this root dB taken as 2 volts. So when this 2 volt signal is entered in the decision making device, so here there is a comparison between this incoming and the threshold value. So 2 is greater than 0. So my decision making device makes in favor of symbol 1. Makes in favor of 1. Or 0 is coming, for example. So the A signal is 0. So here up to this integrator the final value is 0. So the 0 enters in decision making device. So 0 is compared with 0. So it can be made decision in favor of simply 0. So this is the way of direction of binary ASK signal. So here about the description of this reduction of binary ASK. So it consists of product modulator followed by an integrator and decision making device. So the incoming A signal is applied to one input of the product modulator. The other input of the product modulator is supplied with the sinusoidal carrier generator with the help of the local oscillator. So that's why the synchronized or coherent detection is costly. Why? Here we are going to generate this signal oscillator. So the oscillator is costly. So for that, compared with the coherent and non-coherent, coherent is the costly one. And now the output of the product modulator goes to the integrator. So the integrator operates on the output of the multiplier for successive bit intervals, and essentially performs a low pass filtering action. So the output of the integrator goes to the input of the decision making device. So already we discussed the decision making device how to take the decision in favor of either symbol 1 or symbol 0. So already I discussed this one. Now the applications where this ASK is used for a low frequency RF applications and some home automation devices, industrial network devices, wireless base stations, and again optical fiber communication for laser intensity modulations. So I taken some of the applications of this amplitude shift keying, and many are there left. Okay, and references this content of information is taken from the communication systems by Simon Hacking, third edition, and digital communications by Simon Hacking. So these two books are referred for this content of the information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.